Welcome, everyone. Thank you for making it to be with us today on another installment of our webinar series on large language models. Today's another special one. Today's talk will be presented and led by one of our PhazeRo team members. Today we'll have Aseel Rawahi, who is a software engineering lead at PhazeRo. He is a full stack data scientist and comes with a large background in banking and engineering. He has experience in building and deploying application-ready solutions. So without further ado, I will hand it over to you, Aseel, for your what I'm sure will be a very interesting talk.
Thank you, Hisham, and thank you, everybody, for tuning in. So we have our agenda here for today. We will be starting by introducing large language models and how they are built. What are they and how they are built? Then we will go over how we can utilize large language models in our workplace. Then we will look at some of the capabilities of large language models just to brainstorm and find cases relevant in our workplace. Then we will go over the big concern of large language models and how we can build a robust system that utilizes large language models. Lastly, we will look at how this architecture really looks like. So what is a large language model? Here I have some examples of large language models that I'm sure you are familiar with. We have ChatGPT along with Gemini and open source large language model Vicuna. Large language models are a deep learning network that understands language and can perform various natural language processing tasks. So when dealing with large language models, you have two main files. You have your model parameters file and you have your execution file. The model parameters file contains the weights of the model. And if you are not familiar with the weights, think of it as a bunch of numbers that aim to balance the network so you can get the accurate results. The other file is the execution file, and it can be written in any language really. In our case, the execution file written in C and is about 500 lines of code. So after creating the neural network, utilizing your execution file, what you typically do is you feed the execution file your weights, your neural network weights, so that you can start loading the model in your and the network itself. So we learned on a high level how large language models are built, but how do they really work? Here I have an example text. We have PhazeRo is an awesome. So if we feed this text to the large language model and ask it to complete this sentence for us, what the large language model will do is going to break the sentence into tokens. And if you're not familiar with what tokens are, you can think of it as units of text that the large language model understands. So usually every token is about 3 to 4 characters, English characters in length. And it really depends on how you are tokenizing in the first place. But in this case, for simplicity, we are going to say every word represents a token. And then we feed these tokens in our large language model and ask our large language model to predict the next word by utilizing the massive data set that the large language model was trained on before. We take the large language model outputs and add it to the original sentence and repeat the process again. In this case, we have the large language model to predict the next word to be AI. So we take that output, we combine it with our original sentence, and we run the same process again. So we break the sentence to PhazeRo, here's an awesome AI, and then we ask the large language model to output the next predicted word, which is, and at the end, we have our completed sentence of PhazeRo is an awesome AI and machine learning startup. One of the major breakthroughs in AI is this research paper written by Google. introducing a new neural network architecture, which is now the foundation and the basis of large language models, including ChatGPT, Gemini, and others, which is transformers. Transformer attention is all you need. How it works is really by having different processing layers of text. You have two components, your encoder and decoder, and you pass your text in the encoder, and it goes through different layers. The original paper had about 6 layers, but now large language models such as ChatGPT has over 90 layers. The two most important layers in this transformer architecture is the feed-forward, which allows you to predict according to what it was trained on, and the attention layer, which allows the model to understand the text. I'm not going deep into the transformer architecture in this session, since it's a big topic, but I think it's very essential to understand. So we have gone through what LLMs are, how do they work, but how we can train a large language model. You really have 2 layers into this. You have the pre-training layer, and then you have the fine-tuning layer. The pre-trained layer is basically having your large data set, in this case, your X billion data set that you feed to the neural network and train your model on. As you guessed, this process is very expensive and takes a lot of time. Just to give you some insights, Llama model 2 took about 12 days to be trained, over 6,000 GPUs, and a total cost of $2 million. So this is a very expensive process to train a large language model. And the other part of it, which is the less expensive and less time-consuming route, is actually fine-tuning a pre-trained large language model, which is basically taking the pre-trained large language model and training it on a specific task or extending its knowledge base. So this is a really good approach if you have the large language model understanding of the language, and you would like to train it in a specific task or a specific structure. Here is an example on how fine-tuning works. You have your massive pre-trained large language model, and you add certain documents that share a similar structure. In this case, we have the user, and the user has a question, and then the assistant has the response to that question. So when feeding this to the pre-trained large language model, it will look into the similarities between the documents, and it will learn from the patterns within the document. This would be done in iterations, and it requires a good amount of data. An example would be generation of structured reports. You can utilize the pre-trained large language model and its understanding of language to generate reports that are specific to the medical industry. And then later you can ask the large language model to create a diagnosis report. So in this case, you would have a specialized large language model that is trained in your specific use case and data. So how do we really find a use case that we can utilize large language models in our workplace, whether as a professional or as a student? My advice would be first to find a repetitive task. It's very similar to the automation. What kind of tasks that they do every day and someone else can do it for me? If I provide him steps on how to do it, for example, let's say I'm attending a business meeting and I usually create my business meeting documents. And I perform the same steps over and over, and I can easily ask someone else to fill it for me. In this case, the large language model. This would be a very good example on how you can utilize large language models in your workflow. So after you have understood the use case, you need to analyze your goal. You'll start analyzing the goal and what are the layers that you need to achieve your goal. For example, if you want to automate the writing of a business proposal, I need to have a unified structure for my document. I need to determine if the data is actually constant or if the data is dynamic. And other analysis that you need to perform to get to the stage of really integrating the large language model in your workflow. Next, and one of the main elements in your consideration should be the risk. You need to understand the risk. when integrating large language models? Am I dealing with very sensitive data? For example, the automation of prescriptions or managing airline routes. So this is another element that you need to consider when integrating a large language model in your workflow. So to brainstorm a little bit, I know we've gone over how large language models are built and how we can utilize large language models. But to give us some insights of the capabilities of large language models and how we can deploy them, I've listed a few examples here of their capabilities. So the first capability is the text generation, meaning if I input the text and ask the large language model to complete the text with meaningful content, for example, here, once upon a time, and I ask the large language model to complete the text, because this is obviously a story, then the large language model will input or output the story. The next use case is template generation. As we discussed, we're dealing with templates, in this case, invoices. We can ask or we can deploy an application that utilizes large language models to automatically fill invoices for us. Next use case is language translation, meaning we would like to translate text or a sentence from one language to another where the meaning is preserved. And the most common use case nowadays with the introduction of ChatGPT is question answering. Another capability is sentiment analysis. For example, you have your customer feedback and you would like to check if the feedback is positive or neutral or negative feedback. And rather than looking at all the feedback, you can feed it to the large language model, do your sentiment analysis, and then you will have your data ready. One of the most beautiful capabilities for us as software engineers, we love it when a large language model can output the code for us. It's really powerful capability, which allows people who have no coding experience to be able to develop and learn how to develop applications pretty much quicker. So we had our brainstorming a little bit on what are the capabilities of large language models. Now we need to understand what is the big concern about large language models. So hallucination tends to be the major concern. And if you are not familiar on what hallucination means, it's basically our large language model is dreaming. For example, I'm pretty sure you've been in an occasion where you ask ChatGPT to perform a certain task and then it replied with a completely different item that is nowhere near what you've asked for. And this is what we call hallucination. So for us, really, building a large language model application is like constructing a building. When first skyscrapers were introduced, there was the common concern between people if these are big or tall buildings would be able, if they are stable, and would be able to replicate such buildings across the city. So to us, this is very similar to large language model. And once we have more of these out in the production, out in the public, it will make us more confident that these large language model applications are really good in specific use cases or in general use cases. And to us, really, when building a large language model, we need to look at observability. And for us, for you to gain confidence, you need to have observability. So these really go hand in hand together. And by that, we mean in every process that you feed or utilize the large language model, you need to understand what is the input and what's the output. And then you need to look at it from the big picture to gain the observability. And this is a very important element because this will give us confidence that our application is actually performing how we think it should. And the last component here is when large language models first introduced, there was this huge attention on architecture. And the data is actually very, very important. And it's a crucial step in building LLM-powered applications. And the reason for that, if your data is not good, basically your LLM-powered application cannot be anywhere near your expectations. So you have to start with the data because the data tells you really how efficient your system is. And what we have found here at PhazeRo is that when we have more domain-specific data in our large language model applications, it really helps with the response of our large language model application. And this will be one element that you can reduce the hallucination, the typical hallucination of large language models. So now we will go a little bit deeper into large language models and how they are built and how we can build an application that utilizes large language models. Here we have one of the most common architectures in building LLM-powered applications, and it's called Rawahi architecture. And it stands for Retrieval Augmented Generation. And we have it's called Retrieval because we are actually retrieving document or knowledge base in the same pipeline that we have in our application, and then we're feeding it in the large language model itself to synthesize. So our flow usually starts with the user asking a question. And then depending on the user question, we retrieve documents that are in our knowledge base, and we think they are similar to the user question, whether that was in our similarity search or any other way for us to extract these documents. And then what we do is we take the user query along with the documents that we think are relevant to the user question, and we feed it to the pre-trained large language model. And then we ask the large language model to synthesize that response and send it back to the user. That is typically how RAG applications are built in a high level. But what I would like us to do is to actually break the system into 3 different components, and then we can see how we can make every component robust and efficient in our LLM-powered system. So the first component is the ingestion. And what it means actually is how we take the raw document, clean it, parse it, and save it in our data store so we can retrieve it later on in the process. And the next component is the retrieval. And it's basically looking at the most similar document, in our case, the top K documents, and extracting these documents depending on the user query and the similarity between the user query and our knowledge base. Lastly, we have the generation, and it's basically utilizing the large language model to generate our response. So let's start with the ingestion pipeline. And typically when dealing with the ingestion pipeline, we have 2 routes, and it's really dependent on our data base. So for example, if we are dealing with structured documents, it's very easy for us to work around structured documents because we have an expectation of what kind of validation that we need to perform for the document itself to ensure that we are parsing correct information from this document. And this makes our life much easier because we have that expectation. It's not an assumption anymore, it's an expectation that we can validate across our pipeline when ingesting these documents. Next, we have complex documents, and when dealing with documents that contain tables, contain infographics, contain text, headers, it's really difficult for the large language model to understand what's going on in these documents. So our job is basically to clean these documents in a way where a large language model can understand these documents. Another element in the ingestion pipeline is basically adding metadata filters. And if you don't know what metadata are, they are basically a reference to the document that we are parsing in the data store. And that allows us to make our ingestion pipeline or the retrieval pipeline more efficient, because when we have the user question, what we can do is we can filter the documents depending on the user question. So for example, if the user question is in the genre of comedy or asking for a document specific to the year 2020, what we can do is do metadata filtering on these documents and only treat the documents that has the filter of the year 2020, which is a very efficient and robust way of determining or ensuring whatever we're feeding to the large language model is actually what we intend into feeding it. Another component is the document loaders, and we have industry leader structured IO in terms of loading the document and parsing the document in our ingestion or in our vector store. Because we're dealing with large language models, we have a certain context window that we can feed to the large language model itself. So splitting text is a very crucial step in our ingestion pipeline. We need to, and especially when dealing with large data or large documents. So one of the concerns here when splitting the text is to preserve the meaning. So this is one of the crucial elements that we need to consider when ingesting documents. We need to preserve the meaning while splitting the document into different chunks. Another part of the consideration is when dealing with tabular data. And this is a huge bottleneck for large language models. So if you're dealing with a large language model that understands Markdown, one efficient way of utilizing tables is actually along your cleaning and processing pipeline. At the end of cleaning your table, you will transform the table to a Markdown. And what that allows the large language model to do is it will have an understanding and to have knowledge of the full table itself. And instead of just looking at the documents and retrieving whatever document or whatever text that you think is similar to the user question. And this will allow you and help you to generate more accurate responses while utilizing the large language model. Another way, if you're dealing with large language models that are not supporting Markdown, for example, we have at this stage ChatGPT 4.0 to support Markdown, but what if you're dealing with, for example, an open source large language model? In this case, what you can do is you can index the entire table as a node. And later on, we will discuss some more on how documents can be nodes and how we can retrieve specific nodes and feed it to our LLM-powered application, in this case, our RAG architecture. So our preferred solution when dealing with such documents and tabular data specifically is to perform an OCR in that document at first. And our concern here is basically splitting the documents into three different documents. We have our infographics to be in one pipeline. We have our text to be in one pipeline. And then we have our tables to be in the last pipeline. And what this allows us to do is to perform certain cleaning steps very specific to the data type. So for example, if we have infographics, we can run another layer of OCR into that infographic to extract text that the infographic has. And if we have tables, we can run an OCR that detects the structure of the table and then transform the table into the required structure that we would like. Another solution to this is having structured table summarization. And we will go deeper into this. It's basically taking the table and summarizing the content of the table as text. This is a very efficient way when dealing with large language models because large language models are mainly built around text. So for you to take the table and then transform it to text, it will improve your RAG application response. Another way is node references, and node references is basically you having your parent document and then you have your children documents. The parent documents in this case is the summarization of the table, and then the children documents is the document itself, the table itself. And depending on the user question, you retrieve the parent document and you check if it's similar, then you retrieve the rest of the children documents and you listed all of these documents to the large language model to synthesize the response. And this is what we call recursive retrieval. So in terms of how it looks like, we have our headings and footer in this document. This will be extracted out of the document. And then we look at the text, and this will be extracted out of the document and parsed and cleaned in its own cleaning pipeline. And then we have our infographics. We extract the information of the infographics, and in a later stage, we combine all of the pipelines in a cleaned and structured document that we later on feed it and ingest it in our RAG application. One of the most important things to consider is when dealing with tabular data, there is no 100% solution. The issue with complex tables we found are mainly due to headings. We have different ways to create table headings that makes it very difficult to really understand what is a heading versus what is a row or a field in our table. So the best way of doing it, if you would like to automate the process, make sure to have a logging system in your table parsing system. So what that will do, it will give you an observability of what you're actually indexing to your database. And before indexing to the database, you will be able to validate if this is the right information to index or ingest in the data store. And lastly, make sure to document. You will see a lot of occasions where you're actually parsing the documents into the data store, and you don't really have a reference to the clean document. So that makes it very difficult to understand what the large language model is actually trained on if you only reference to the raw document. So you need to have that kind of reference of the raw document, the clean document, and the data store itself. So in here, we have one example of recursive retrieval utilizing an open source framework called Llama Index. And as you can see, here the user is asking two different questions. So what we really do is we split these two questions into two different questions, and we go into our pipelines for these specific documents. For example, we have our Boston pipeline that includes the Boston node, indexing node, and the document agent itself. And then we retrieve all of the information separately from each document or from each node. And then at the later stage, we compile and synthesize the response. And this allows us to have very specific information being parsed or sent to the large language model. For example, we can utilize this when dealing with tabular data because I'm sure you know we have a lot of tables that share a common heading or common columns. And the main differences between these tables might be just the year. For example, we have the same table that belongs to year 2019, and then we have another table that belongs to year 2020. While they share the same headings, they are completely different documents. What we can do, we can utilize something like this, or we can go back to our meta data filtering processes. So you will see a lot of techniques here. It's very dependent on your data, and you have that flexibility of choosing what kind of technique to embed in your system. Another important component in the ingestion phase is embedding fine-tuning. And embedding fine-tuning is a very great way in increasing or boosting your RAG application efficiency instantly. We have found the performance increase of between 10 to 20% when fine-tuning embeddings. And basically how you do it is exactly by establishing data sets. So you're going into the regular machine learning flow of having your training data set, evaluation data sets, and lastly, your validation. You will be asking on how I can create my own data set and utilize such a flow when building LLM-based application. The industry standard in this case is utilizing ChatGPT 4.0 to create your training and evaluation data set. And what that will do, it will allow you to fine-tune the model, the embeddings model, and also utilize the same data set in your evaluation stage, which we will go over later on. So that was high level on the ingestion pipeline. And for the retrieval pipeline, which I really believe is one of the most important components in RAG applications, we've discussed recursive retrieval, which is also called small to big retrieval, where you have your parent chunks referencing your children chunk. And the parent chunk usually is a summarization of the main or the children chunks. And this recursive retrieval is very fast and allows us to perform very specific retrieval of our documents. Another way of retrieving is window-based retrieval. And for example, in this case, we look at a certain sentence in our data store, and then we expand the window. So for example, in this case, first of all, we're looking at the sentence in red, and then we expand, moving upwards and downwards on every sentence that we have, or we have a chunk that we think is very similar to the user question. And it's a very good way in reducing the noise in the document, where we might have a paragraph and then another paragraph that explains something completely different. So what this does, it looks at your window level, and then it will stop when it thinks that the meaning is no longer consistent. Another way is hide, and it's hypothetical document embeddings. And what this does really is, when you create, when the user inputs his query, you immediately create an embeddings, hypothetical embeddings in a response of the user question while utilizing the prompt in your system. And this is a very efficient way of looking at the similarity or looking at the documents in your database, because you will be doing the similarity check and relevance with the user question, and also the relevance with the hypothetical embeddings that you've generated. Another way or technique to make your system more robust is similarity check versus reranking. I just want to explain what reranking is and how it's different from similarity. So in your similarity search, you have your data store, vector data store, and you have your nodes being saved in the data store. And the placement of these nodes are really depending on the meaning between every node. So for example, in here, we have documents that are very close in meaning. So we parse them or save them in the data store in a place where they are very close to each other. While reranking, we have context in the user question itself. So in the similarity search, we don't have any idea on how the user question will be placed in here. But with the reranking method, we have that ability to look how our user question is similar to these documents. And one of the downfalls of this reranking is it's actually slower than running the similarity search. So how do we usually utilize such a solution? What we do is we run the similarity check first. We get our top K documents, meaning in this case, or for example, we have our 8 documents. And then we take these 8 documents and we create embeddings for the user question. And we do the reranking and the similarity search between these 9 chunks, which is the user question along with the 8 documents that we retrieved. And then we re-rank the documents that we retrieved from the similarity search according to the relevance between these documents. Another way is doing semantic search on retrieval. And this is found to be one way to solve hallucination. So if you remember in your RAG application, you are taking the most relevant documents with the user question and then feeding it into the large language model. What you can do is actually take what the user has inputted along with the documents and run a semantic search on these and see if these are actually relevant to each other. And you can define a threshold that can utilize or can tell you if this is really similar or it's completely different meaning. Another way is you have your query engine, which is basically multi-document retrieval. You have a query engine to map you to the different nodes that you think you should access to depending on the user question. And another way is the maximum marginal relevance, which is another way of doing similarity. So we've went through the retrieval, the ingestion pipelines. Now our main component that utilizes the large language model is the generation pipeline. And mainly in here, you're very focused in prompt engineering. You have very examples or templates on how you can create a prompt to train the large language model to perform a certain task. So listed here is a few examples: zero-shot prompts, one-shot prompts, few shots, and chain of thought. And mainly in here, what you're trying to do, what you're trying to accomplish is to give examples for the large language model that it can utilize to generate a response. For example, if I would like a large language model to send me a response in a specific format, I give it an example of a specific format and my reasonings behind generating such an answer. And then the large language model would utilize the structure and the reasonings to output a response. Also, one way is parameters fine-tuning. You have your temperature, you have your top K, and these all of the fine-tuning methods, parameters fine-tuning methods that you can utilize to make your system more robust. And this is really dependent, again, on your data. And also the models, if you're dealing with sensitive data and you don't like exposing the data into the cloud, you will be utilizing a public source models or a fine-tuned model for your specific use case. So the generation pipeline is very dependent on the model itself as well. And we have other techniques such as chains and agents that we can utilize in building large language models. And here I've listed some templates for prompting techniques for RAG application. Next, we have evaluation. So we got into a stage where we have our system, and we have all of our components, our data is good. So how do we really evaluate our system, and how do we really gain confidence that our system is actually performing? And in most cases, you will see that when dealing with models, it's a black box, really. You have your input and output, and you need to understand what's happening in between. So the way we like to consider evaluation really is not a component. It's an end-to-end process, meaning if we look at different components in our RAG application, we need to have a layer of evaluation in every component. And the evaluation needs to be matrix-based, and that allows us to have a baseline of how our model is doing. Is it actually improving, or actually it's decreasing in performance? So, for example, evaluation of score of 80% is basically useless in our case, because we don't understand what that 80% really means. So our evaluation score of 80% match references is good because it's actually mapping that metric into a certain criteria, and we have our evaluation number that we can utilize to see if our large language model is performing. And another way is to have flags. For example, we can look in our system and we have certain flags that can act as guardrails. For example, one of the common guardrails that we implement is the moderation guardrail. And what that does is actually looks at the user input and see if this user input is actually compliant with our requirements. For example, we don't like to deal with data or questions that are specific to math, for example, and we would like to extract this information from our large language model pipeline. So in that case, when we detect a question that is not relevant to what it's trained, we can immediately set the flag of, sorry, our system is not trained to serve this purpose. Also, the hit rate, you can identify loss function, and this will be for the embedding evaluation. And then you have the exact match, which is an LLM evaluation. So you can have different evaluation matrix, evaluation criteria for different components in your system. So what do we usually look after when dealing with LLM-powered applications? We look at correctness, and it's basically, is our generated answer is exactly like the reference answer. We look at similarity, is the retrieved documents match the user query. We look at faithfulness, the answer is within the retrieved context that we've put, and also the relevancy between the context and the answer. All of these evaluation criteria could be changed depending on your use case and your data as well. But here are some of the common evaluation matrix that we utilize. Lastly, we have human feedback. So people usually, or when engineers like to construct this system, they go immediately and look at the human feedback. But what we can do is we can implement more criteria on the top, and that would allow us to gain insights before having that user feedback, and utilize the user feedback to assure that our evaluation is actually solid. One evaluation popular library is Ragas, and this library gives you the ability to measure the evaluation and input a number that you can utilize and reference later on in your pipeline. So we have context recall, we have context precision, we have precision, and we have faithfulness score, which is the matrix that we've discussed before. And if we would like to compare between different responses, what kind of matrix that we can utilize, or evaluation that we can utilize. Mainly, we look at coherence, conciseness, accuracy, harmfulness, helpfulness, and lightness. And this is, again, we can utilize open source tools or custom tools. For our case, we have Langsmith that can allow us to see and evaluate our large language model response. And also we have LangServe that allows us to deploy such a solution. Now, we've implemented a lot of techniques, implemented a lot of ways to evaluate the large language model. If we would like to take it a step further, we can utilize a large language model to evaluate our large language model application. And what this would do is basically it would look at the user question and will look at the response of our LLM powered application, and then it will evaluate if this is a good response or not. And this is if you would like to take another layer and take another step in your rank-based applications. Another way is to have a conversation between large language models. For example, I'm sure you've been in a situation where the ChatGPT have inputted or created an output which is not relevant, and then you provided more instruction for ChatGPT to create a response that is actually relevant to your question. And this could be the case here when we have conversation between two large language models. We can have the first large language model to create the output, and then the second large language model to instruct the first large language model in what kind of output it should provide. So how would our architecture would look like. And this is an example architecture. First of all, you would have the user input, you would do your authentication in your application, and then you would have your input guardrail. And this is what we've discussed. Some inputs we don't like to process in our pipeline. So we extract these out and actually send the response immediately that this is not a document that our application, or not a question that our application is actually trained on. And then we have our query rewriter. For example, when dealing with user input, usually, or in some cases, the user does not provide a lot of context or a lot of information. So the large language model itself is not aware of the user question. So what we can utilize is we can have a query rewriter to make the query of the user more concise, so that when we go in later stages of our pipeline, we will be able to respond with a much appropriate answer to the user. Along with various components, as we discussed, you'll be seeing this is on a high level how you can create an architecture around large language models. So where to start? I would really advise to start with documentation. Look on how you want to construct your application, what kind of use case you are trying to solve, what kind of data that you have. And then start with establishing a feedback loop. And this would allow you to iterate much quicker in your RAG application and make your RAG application very specific to your domain data. It will be very domain specific. And in this case, when you be in that stage, you would need to establish an R&D team that looks at different small marginal differences in your RAG application that allows you to boost the efficiency of your RAG application. And also the most important is you need to set evaluation. And again, your evaluation should be metric based. You need to measure an actual metric, and that metric should map to a criteria that you are very concerned about. If you want a quick wins in your RAG application, focus on retrieval, and it's found to be the most important component in RAG system, not the generation. And bring focus back on data. Look at the data. Again, if you don't have a solid data, don't expect your system to output an accurate response all the time. You need to think on how your data looks like and how you can utilize the data in your large language model application. And lastly, iterate. You'll need to iterate over and over so that your system becomes robust. You will find some edge cases that you can build your system around and make your system actually more efficient. As we reach the end of this webinar, I thank you all, and I would like to shift the focus to our next LLM course, which is utilizing AI to foster innovation in the financial services sector. The registration is now open, and you can use the QR code if you'd like to have more information for this specific course. Other than that, I think we've concluded our talk, and we are open for questions.
Thank you very much for a very engaging talk, Aseel. So yeah, at this point, we'd like to open the floor for any questions. So if you have any questions, feel free to just raise your hand and unmute and go ahead.
Thank you very much, Mr. Aseel, for this great presentation. I just have a question regarding using a large language model with English, which is the pre-trained model, as you mentioned earlier, that takes significant amount of money and time, and versus using sort of a large language model trained on Arabic, for example. Is it more efficient to train your own model on your own language, or just use another tagged on LLM to do the translation, like I've seen others do? Given the fact that there's sort of a gradient where a lot of resources and money is done on English, of course, because this is where the companies are that make this, versus sort of smaller companies in the Gulf region? I just want to see what's your take on this. Thank you.
Yeah, thank you. It's a great question, really. And I think it really, again, depends on the use case itself. Of course, building a model that involves feeding different data sets in Arabic and then training the model in that specific data set, it's gonna give you a much better responses. But it really refers back to your use case. Do you really need that kind or that level of correctness in your system? And one way to reduce all of this cost is to utilize, as you mentioned, a large language model to do the translation. Or what you can do is actually use a pre-trained large language model that understands the language and build a RAG application around it with no cost, really. I hope that answers the question.
Excellent. Thank you very much.
We have a question in the chat from Yusuf. The question says, in order to train our LLM, we need big data, and most likely there will be some points that are conflicted. Is it okay to have these conflict points of view, or will it affect our LLM performance?
Yes, so actually, when you're training the large language model, again, we emphasize a lot on the data. The cleaner the data, the better your large language performance is. And one way of doing it, one of the reasons why you see a lot of companies like Twitter and Reddit closing their APIs is that you scrape the internet, you extract information from web pages within the internet and build your data set from the internet itself. And then depending on your cleaning pipeline, you will structure the documents and the web pages in a certain format, and then utilize that to train the large language model itself. Is that answers the question, or? Sorry, I think I might went out of topic a little bit.
Hopefully that answers your question, Yusuf. If not, please feel free to unmute or respond to chat. I don't know if you have access to the chat on your screen, Aseel, but the response was, so would we keep them within our data set or shall we remove them?
So what happens is that when you train the large language model, you will have your weights ready. So the model itself will be trained in that specific data set. So you don't need to keep the data set, but you would need to keep it later on in later stages. For example, what is happening right now with OpenAI, what they're doing is that they have their model, they created their pre-trained large language model, and they utilize human feedback to iterate over it. So they will fine-tune it on every time, depending on the feedback from the users or the feedback of the system itself. So it's very efficient for you to keep the data, but the large language model does not need access to your data to run, if that makes sense.
I think that answers the question. Yusuf responded. Thank you very much. Do we have any other questions from anyone else?
May I just say a few words? I appreciate from PhazeRo and on behalf of the American University of the Middle East and UC Berkeley Amena Center, I highly appreciate all we are doing together with PhazeRo and hopefully with the support of Dr. Abdullah from AUM, Masood and Leila from PhazeRo and UC Berkeley. We will do much more, and we are looking forward for much more disseminating kind of, I would say, webinars, and I appreciate the good lectures, Aseel. It was fantastic, and look forward for the next lecture. We will inform all of you. Thank you all.
Thank you, Dr. Yahya. We are very grateful. Thank you all.
Perfect. Thank you, Dr. Yahya, and thanks everyone. I don't think we have any other questions in the chat. As mentioned, this is one lecture out of our multiple lectures that we've released so far. You will find all of them on YouTube. in addition to this one. And as Dr. Yahya mentioned, we will be having future iterations of this webinar. So stay tuned and we'll share the information with you once it's available. Thank you, everyone, and have a good rest of your day.